So we want to welcome everybody to this this edition of the Networking Channel. We've got, I think, a fabulous program here for the next hour. And again, as always, we're going to stop. Got a hard stop on the hour. And today's session is actually a pretty interesting one in the sense that, well, the topic is, 40 years of internet history. What have we learned? An industry perspective. And some of you may have been online, I guess it must have been 3 weeks ago, maybe 4 weeks ago, where we had a panel with a similar title about 40 years of internet history, what have we learned? And I think it might be fair to say that that panel took a little bit more of maybe an academic point of view. And that was actually based on a workshop that had happened earlier in the year. And we received some comments from folks afterwards. Well, maybe some folks in industry, yeah. So from Christophe, my phone absolutely lit up during that last one saying, well, from an industry point of view, I'd look at it this way. And emails came in about that afterwards. And we thought, well, that's great. We should have another session where we talk with folks in industry and get this industry perspective about what's been learned in 40 years, because certainly how services are provided are probably very different than, clearly very different than in the sort of, 1990s era where things were still pretty much point to point. We didn't have sophisticated distributed edge infrastructure and things like that. And so we thought it would be a great opportunity to sort of continue the discussion that happened there and take an industry perspective here. So that's what we're doing today. We're going to introduce our panelists in just a second, but Christophe.
Yeah, and just to remind you, Marwan forwarded me an article from IMC 2020 a few days ago that was saying that only 10% of the internet traffic is going through the big I internet anymore, and then 90% is sucked by the hyperscaler network, like the Microsoft, the Googles, the CDNs, and so on. So it's really different network today, and that's what we want to discuss today.
Right, and that was I think that was Ethan Katz-Bassett's paper about sort of the continued flattening of the internet and the percentage of edges that are reachable without going through a tier 1 or a tier 2 ISP by some of the major providers that we see sort of sitting around us here. Okay, so with that, the way we're going to be doing this is we've 4 amazing panelists here today. We're going to introduce them just very quickly, and then we're going to give each of them an opportunity for sort of 5 minutes of comments and statements on this topic, and then we're just going to open it up for discussion. So maybe I'll start off and introduce Nandita Dukkipati, who I think many people know. She's a principal engineer at Google. Her work has been focusing a lot on data centers and on delivering end-to-end performance for applications and services. She's done work in congestion control, telemetry, and different ways of making better use of bandwidth and smarter scheduling systems. So Nandita, welcome. It's wonderful. Great to have you here.
Thank you. Super happy to be here with all of you. Yeah.
Great. Christophe, you want to introduce Marwan? You're muted.
No, I realized that I didn't realize you wanted to introduce everyone first, and I thought that you wanted to introduce people before they talk. So what about Nandita? You go and you give your talk, and then I introduce.
Okay, that sounds good.
Okay,
Nandita, you're first up, and I think you've got one slide, right? You wanted to share your screen.
That is correct. Yes.
Great.
Just let me know if you're able to see my screen.
We can see it.
Okay, fantastic. So the slide that I want to talk about is this. So hi everyone. First of all, super happy to be here and reflecting on the things that we've learned, through deployment experiences, etc., and in our networks, and relate it to the 40 plus years of what's been happening in the internet. So I wanted to talk about these 4 points that are on the slides out here. To me, one of the amazing things when I first joined Google, one of the first charters that I was actually put to work on my startup project was making the web faster, right? And this was, and it was amazing to me at that point because we were talking a lot about how performance is no longer probably as important for networks and so on and so forth, or a lot of things that were to be done in performance were done, and what we care about are availability, reliability, and dependability, and all of those things, which are super important. And yet here we are actually tasked with making the web faster, right? And I realized over time that speed and latency is something that users will never stop caring about. Users are just more, as Larry Page used to say, that users are just more forgiving if whatever you serve is really, really fast, right? So speed was critical. And over the years, it just struck me that, when we talk about making things faster, making applications faster, whether it's in the data centers or the internet, there is a common element to it. Many applications care about the tail latencies of the application level of whether it is a video chunk that is being streamed over the internet, or it is a highly distributed, synchronized application running in the data centers, right? That tail latency, reducing that distance between the median and the 99 percentile, etc., seems to be a very important aspect of different applications, whether they're running over the internet or over the data centers. It has amazed me that our community, the internet community, is actually risen up to the challenge and evolved the protocols, right, across the layers, whether starting from what was called Speedy. This was more than a decade and a half back, whose learnings are now taken into HTTP2, right? And then there is the Quick protocol, which makes changes at the senders and receivers. There have been a number of enhancements to the transmission control protocol, or TCP, with respect to faster loss recovery and so on and so forth, right? And then there are enhancements to newer congestion control algorithms such as BBR and so on and so forth. But the underlying element in a lot of these evolutions is how do we actually make our applications faster over the network? And at the same time, our community is also recognized at a problem that was getting worse at a time, famously named as the buffer blow problem. And we've risen to the challenge as a whole to actually spew out new things like new algorithms, active queue management schemes, like Cordell and FQ Cordell, Choke, Pi, and more recently, or probably not as recently, the L4S efforts as well. So basically, whether one works in the data centers or whether one is working on the internet, speed and delivering that application up as quickly as possible, I think, continues to be an important thing that we've seen, and I suspect that we'll continue to see actually going forward. The second aspect that I wanted to talk about a little bit is intelligence at the edge. I think Jim and Christophe seeded us with some questions like, we're interested in why you've supported some of the changes, and one of the, or the original tenets of the internet, and one of the original tenets was intelligence at the edge, right? It amazes me that, when we went to the data center world, one would think that, given that we could actually change anything in the data center, the senders, the receivers, the switches, routers, seen that we would revisit this TNet. But over the years, it occurs to me that even in the data centers, actually, we gravitated towards this original TNet of the internet, where there is intelligence at the edges. And there are a number of reasons. I'm going to mute someone. There is noise. Oh, so there are, and even in the data centers, what observation is the end systems, whether it's the end hosts or the NICs, right, have evolved faster. Christophe, do you mind muting yourself? I think there is some noise. Thank you. Yeah. And even in data centers, this TNet is actually held up pretty well. And reflecting on why that is so, one of the reasons, has been that it's much faster to upgrade software on the end hosts and servers. Probably iterate on it, etc. So even specialized networks like data centers have actually gravitated towards or embraced the TNet that the internet started out with, intelligence at the edges, right? Whether we talk about traffic management or even load balancing schemes, a lot of the things are actually controlled by the hosts, by the end systems, by the NICs, and so on and so forth. Centralized policies, such as software-defined networking and SDN and different flavors of SDN have also taken off, more so in the form of centralizing the policy that would operate the network, right? Whereas a lot of the data path is still distributed and driven at the edges. So that was something that just struck me, that actually stuck even with the data centers, but came in from the internet. I want to talk a little bit about the evolution of networks. This is something that something that I really wish for the internet to have more of, right? One of the things that has been powerful in the data centers is really the power of iterative and incremental changes. The ability to be able to put up an experiment out there and observe how things are evolving and to be able to iterate on it. The internet has definitely has had some aspects of it, right? And maybe certain, but this is something that I wish that we could do more of in the internet, because just the ability of putting out an experiment out there and seeing the impact that it has on the users, right, really gives us a lot of data on what are the next steps, us meaning the community at large, a lot of data on what next to do. This is something which has been much more easily doable in a data center environment, but I wish that we could actually do more of it even for the bigger internet. The final point that I want to touch on is debuggability of the networks. I think our networks have evolved a lot. The internet and the data centers have evolved quite a bit, and yet sometimes the fundamental question the user or a workload comes up with, my network is slow, or my application is slow, and we think it's the network. And it continues to be quite a toil, quite a hassle to be able to pinpoint what exactly in the network is slow. So I think, evolving our networks to be more easily debuggable, right? This is something that I, wish that we had it in the baked in some aspects of the design of the network. Debuggability, in some sense, the internet is the victim of its own success. It grew so large that actually it is sometimes hard to debug things in this large distributed system. There are some aspects of it that are getting easier. For example, recently, we've been the community is talking about more explicit forms of signaling from the network to the edges that's going to carry back more information than, say, a 1-bit ECN. I'm hoping that multi-bit signals such as that are not only going to be helpful for traffic management, congestion control, but also for end-to-end debuggability.
Okay.
So that's all I have to say today. Thank you.
That's great. And I've seen a couple of comments and multiple questions already come up. So I'm sure we'll get back to some of these. So our next speaker is Ramesh Sitaraman. Thanks for unsharing there. Ramesh is both a faculty member at the University of Massachusetts and known as one of the principal architects for Akamai Technologies, where he contributed to the designs of the early and later CDN and also their streaming services as well. So some of you may remember actually about a year ago, Ramesh gave a really great networking channel talk, which has been recorded and archived so you can watch it on edge computing and Akamai. So Ramesh, welcome back.
Thank you. Thanks a lot, Jim. Really happy to be here.
Christophe, will you mute your mic? Okay.
I wanted to spend the 5 minutes just talking big picture, sort of looking back over 25 years as someone who's been trying to build a business and also technology on top of the internet as an overlay. And really, I think this actually, tailors to what Nandita just said. Back in the early days of CDNs, when we were building CDNs, you should remember that the internet was very different back then. There was no such thing as DevOps. And we were actually like building these huge distributed systems, figuring out things on the way. How do you deploy software to them? How do you run 100 data centers on the internet? So mostly we were playing it by the ear. And we signed up our first customers for CDNs back, big customers in 1999. And the inevitable happened. Something didn't work. They called, and you soon realize that when a big customer calls, we used to call big customers whales, and they say, my users can't get to the content, what's going on? And if you give them a blank stare and say, it could be us, it could be you, it could be the internet, it could be the ISP, it could be your servers. That's not a good answer because they really want you to know you're the expert you need to know. So we started a project called Whale Watch back in 1999. And the goal of that project was very simple. Can we find problems before our customers and fix them before they call us, right? We thought we would solve it in a couple of years. Unfortunately, it's still an open problem. The problem is that, we've gotten better with tools to do this thing. But the internet has also gotten much more complicated. The end result is that a single transaction, could come into the edge. It could go to a peer. It could go into a cloud. It could go into the origin infrastructure of the customer. It could interact with, half a dozen systems along the way. And it's nearly impossible to really figure out quickly and efficiently what the root cause is. And this is still like a huge problem. We talk about sort of the decentralized layered architecture of the internet. That's great, but it makes debuggability extremely, extremely difficult and an unsolved problem. And it's still embarrassing when a customer calls and says, what's going on, and you know just a little bit more about it than them. So I want to say that this is actually a big problem. So I want to keep this high level, but I can kind of dig into some of the details more. I want to bring in the perspective of somebody who's building a business on top of the internet and looking down. Even in the early days, it was clear that the internet doesn't work like it should. BGP does crazy things with routing. There are lots of issues with the internet. And of course, it's always good to think about how to fix those issues. But I want to also make the controversial suggestion that, we always used to think that bad network is good business, because most of our best ideas came from actually trying to fix what is not working. I know this might be a little controversial, and this used to be our answer pretty much in the early days. I mean, if something isn't working, we'll just build an overlay, right? So, and that's really the origin of a lot of things we did. For example, BGP, the fact that it doesn't do performance-based routing or throughput-based routing, we built an overlay to solve that problem. And that's kind of the origin of overlay routing. We built those overlays back in 2000. Same thing with live streaming, network level multicasting didn't work well for various reasons. So we built application level overlay networks to do live streaming, and it still goes on that way. Security wasn't, was problematic on the internet. So we built security on the edge. And that, we started building some of these things some 2 decades ago. And really what the perspective I want to give is, yes, the underlying internet has problems, but it's also an opportunity for us to build things on top of it. I want to keep this pretty high level. So, there has been a lot of discussion about the internet, and maybe even some people saying, internet doesn't route money. That's one of the problems with it. I want to actually post the opposite side of it. The internet actually does not come with a business model the way it's architected. And that gives us the freedom to kind of innovate on top of the internet. I like to talk about the CDN business model, which we came up with some 25 years ago. We started out in a more typical business model of being a caching provider, like building caches and selling it to ISPs, but that wouldn't work for lots of reasons. So we flipped the business model on its head and we became the middle. So where the CDN actually sells to the application provider and the content provider and pays the ISP. It's a flip of the business model. And the internet actually allowed us to flip the business model in a lot of cases. We built edge computing really early, but the business wasn't there. I think one of the things that we should realize is that the evolution of business innovation and technical innovation go together. And we have to think about that in a clear way. And the internet itself, one of the big advantages of the internet is that it allows innovation on the business side. And that's important because, for example, to take other examples, P2P has been around for a long time with a lot of great research, but it never made a big impact in industry. In fact, P2P content delivery was invented the same time as CDNs, and the impact of P2P is very little. Why is that? Because there is business that plays a role in it. So I will stop here, and I'm happy to kind of go down into any of these different paths. But I think the fact that the internet doesn't come with a business model is actually an advantage.
I'm sure we're going to come back to the business model aspects, and both you and Nandita talked about debugging. So I'm sure we're going to come back to that and building infrastructure on top and debugging that. Dina, I think you're next up. Christophe?
Yes. I don't know why I have to introduce Dina, that I don't know very much. Nice to meet you, Dina.
Good to meet you, Christophe.
Sorry, they've been working together for longer than either would probably care to admit, right? So.
Yeah. I know Dina since she was born, at least to
academically speaking.
To academic life. So, after working many times in the same company with Dina, including Sprint and Intel and Google, Dina is now working at Microsoft, where she's an innovation and engineer leader in computer networking, wired and wireless. She's currently leading the mobile packet core software engineering organization of Azure for operators, with team everywhere around the planet. Good luck, Dina. That's why you never sleep. Nandita and I are discovering that now, okay? Dealing with 24-hour time zone.
Yeah.
And early in her career, I said that already. So go ahead, Dina. Your experience very valuable with us, given your experience in multiple companies and your early academic life. Thanks.
Thank you, everyone, and thank you for the invitation. You know, for me, first of all, I don't have slides. Maybe it's because I don't sleep. But the one thing I wanted to focus on is a question that was sent to us by Jim and Christophe, which is, what is your main driver when designing a network? And I just wanted to bring a perspective, you know, across 3 different types of networks that I have been involved in designing. The internet started as a best effort service. No, it was supposed to be around connectivity, and 30, 40 years later, it's actually fueling everything that we do in society. We have financial institutions, healthcare institutions, governments, emergency first responders, relying on the internet to work, and it's different versions of the internet that each one of those customers or consumers they tend to interact with. So as Christophe mentioned, I've worked in a number of different companies, touching different bits of networking, that may or may not be directly connected with the design principles of the internet. And I just wanted to give you 3 such examples. When I was at Intel, the Wi-Fi was taking off. Right now, we are taking Wi-Fi for granted. At the time, it was just about, wireless connectivity to the internet from end devices. As Wi-Fi started moving into the enterprise space and potentially, replacing wires in situations like manufacturing sites, or supply chain places where you're essentially creating equipment, you're building cars, you're doing things that require connectivity for something to be accomplished. As a result, it was obvious that Wi-Fi by itself, given the shared spectrum and the CSMA/CA access medium, it was not sufficient to provide any kind of guarantees. There was absolutely zero guarantee that you would be able to get a minimal amount of throughput through these networks. That's when, in support of services that aimed to provide some kind of quality for access wirelessly, centralized controllers came to place. And that's where Aruba, Meraki, Cisco innovated significantly, where the idea was that, you needed a central brain that was going to try to understand how to adjust in practical terms, the frequency that these access points were going to use and how much power they were going to emit in order to spread the clients as well as possible to enable, some kind of quality availability of service. On the before side, like Nandita mentioned, centralized controllers came to the rescue in order to be able to provide service level agreements for end-to-end connectivity across a network that was software defined. So the principle being, that the routers themselves were not going to make independent decisions, because that's difficult. It's difficult to actually control the result of a number of entities when they are independently choosing what to do. It's a lot easier to control the quality of service of a network when you are providing them with the guidance that they need in order to be able to accomplish a particular optimization objective that is at the core of the service that you're going to deliver. So, long story short, the internet provided the foundation for all these use cases to emerge, but the level of centralization was absolutely necessary in order to be able to deliver performance and guarantees for the service that runs on top of it. So now I decided to pick a little bit of a different spin here and give you some visibility into the work that I'm doing right now. As Christophe said, I'm leading the mobile packet core team inside Azure for operators. What this means, for those of you that are not familiar with cellular technology, is that there is a very intentional shift in the cellular industry for the monolithic appliances that used to terminate established sessions and enable packet sessions, for the different handsets that connect to cellular networks. They are moving from a monolithic implementation that was part of the 4G, 3G, 2G into containerized microservice-based implementations. So here you see networking concepts materializing in distributed systems that have to enable a particular task, which is every mobile phone that connects to a cellular network needs to be able to get authenticated, needs to establish a session, and needs to be able to access internet services as a result. The result that has happened out of this decomposition is now that you have a 500 container network materializing on top of data centers that run on off-the-shelf compute platforms that need to accomplish a very, very complicated task. They need to be able to establish a session by going across multiple components that have 3-letter acronyms that are multiple, and they have to do this within a certain latency requirement. So, Nandita talked about tail latency. In this particular case, if you do not manage to establish a session within a certain number of seconds, that session is not, established, and it has to be retried. So I have had to work a lot on trying to find out how to properly decompose a problem like this, but not decompose it to the extent that it's no longer serving its purpose. In practical terms, you need to find the right microservices, how to collapse and how to allow independent operation of those microservices in order to be able to reach that latency requirement, that throughput requirement, and of course, the availability and resilience that such networks need to have. No? In some cases in the past, actually, we have had issues with telecommunications operators that were not able to carry 911 calls. So, police and emergency first responders are not able to use the network because suddenly you made a mistake in the way you defined availability or performance for the component that you're essentially providing in support of those services. So long story short, when it comes to designing a network, for me, it's fundamentally needing to understand the problem that it's trying to solve and its requirements. There is no such thing as distribution is, the right solution, or full centralization is the right solution. I think we really need to deeply understand what are the requirements that the network meets. We need to design for all kinds of failure. Assuming that things will work is probably, 10% of your work. The majority of the work is in assuming that everything is going to fail and preventing against it. And just to tap onto what Nandita and Ramesh said, observability becomes critical, because if bugs will always sneak into production environments, they are going to have probably the worst case effect that you were trying to avoid. And as a result, being able to diagnose those issues is important. The stance that we take in the telecommunications industry is that we need to mitigate as quickly as possible and figure it out afterwards. But some of these problems are very, very complicated. So the problem that Nandita and Ramesh were pointing out materializes also in this type of microservice installations, that we are essentially rolling out in major telcos across the world. So hopefully this was 5 minutes and I can pass it on to the next one.
You're muted.
You forced me to mute and I muted, you asked me to unmute. You need to make your mind, okay? Thank you very much, Dina. It was a very good presentation and indeed 5 minutes. Thanks a lot and very clear. So Marwan is our last speaker. Marwan is spending his life between Cloudflare, that you all know as one of the major CDN providers, with Akamai. Maybe Ramesh will disagree with that, but that's a very big CDN provider. And Marwan is also has also an academic position at St. Andrews Universities, and he lives in London, actually. So Marwan, you have the floor for 5 minutes.
Thank you. And I'll try and keep it under 5 minutes, actually, in order to leave even more time for discussion. I do have a couple of slides that I want to share, only because there are diagrams I think that might be helpful. So first, I'm going to start out by saying everything from 3 weeks ago, the other panel, I finally sat down to watch it yesterday. Everything is true, but with maybe 1 or 2 small exceptions, and it's worth going back to revisit that one. And I'm gonna say even further. I'm humbled in this audience, I have to be honest. Everything that you've heard so far is absolutely true. So when I sat down, I thought, sort of anticipating that there's this sort of common set of problems and perspectives. I actually like the perspective about the internet doesn't have a business model and so on. I tend to agree with that one. Observability, debug, all of this matters. Centralized control. It's very much about solving problems. If you think about the internet, being as far as I know, the only global infrastructure and the most critical in so much as it's a dependency for all the other critical infrastructures increasingly. So, and customers come with different problems, multiplexing the different kinds of services. So with that, I think there are 3 slides I think I want to try and hammer in on, if I may. Oh my goodness. Where is here it is. Okay. So the first is this.
We can see you.
You can see me. Can you see the slides?
Yes.
Okay, perfect. So a lot of what we hear about in industry or what you'll hear about is focused within the data center, which I've kind of represent as just a single edge computer here and is not fair. Or within the system itself. So a bunch of data centers that are machines that are connected to each other across a wide area, oftentimes the globe. And I think this image is particularly important because we always talk about the end-to-end principle and is it preserved and how does it change and so on. To be honest, I think, Dina and others have hammered in on this. The foundations of the internet are so incredibly resilient, so incredibly visionary, whether by intuition or by design. It's miraculous that we can do the things that we do to this day. Sure, we were missing a control plane, but people built one as needed. And one thing I'm pretty sure is common among all of the operators on this side of the fence is you always start with the tools that are available. At some point, you might outgrow them and start to write your own, hopefully feed back information to the wider community so that we can learn from it and so on. But the end-to-end principle, in a lot of ways, still exists, just in a slightly different form. So if we talk about the edge services, the client connects to the edge. Very often from the edge, you might reach out to other services that are somewhere outside of the system. You might actually pay additional money, or the operator itself might decide to use its own infrastructure internally because it has properties that aren't possible to guarantee on the outside. But at the end of the day, the internet still exists the way that it was because it's a good design. But then there are other things that we need to think about. What are the things that we missed? Where's maybe the technical debt, in a sense, that we're paying for? I think you've heard a lot, but I want to change direction, and I think I want to build on a lot of what we know to think about the look ahead. And on that, I'm going to say 2 things. The first is with respect to localization. And I'm not using the R word here, regionalization. I'm saying specifically localization needs a solution. For those who are unfamiliar with the new IP proposal that went in front of the ITU, I guess about 4 years ago now, ISOC did a really great job of picking it apart and trying to explain why so many ideas in it were problematic. But they're not going to go away. Being the critical infrastructure that this is, and the global infrastructure that it is, I think it would be naive of us to think that a lot of people who have nothing to do with the internet's design and operation are going to try and guide the way that it exists. And, no fault of anyone, there's no judgment here. People have genuine, valid concerns. One of the ways we can address them is by improving transparency. That's great. But I got to be honest, this one scares me a little bit. Right now, when we talk about localization, there are effectively 2 solutions, which really come down to having no other way to provide service isolation. One of those is logical, right? We manipulate the DNS and the routes that are available in the world in order to direct traffic to different places. And the other one is physical. If you happen to have hordes of money, you can put up new buildings and lay down new cable. It's a viable solution, but I worry it's not one that scales, and it's certainly not one that everyone can take advantage of. So what do we have to do to make up the difference? Now, one version of this is, I work on the design principle that data should be free to travel anywhere. And the immediate counter argument is, yeah, but people won't buy into that. They're never going to put up with it, and so on. And look, the history is ripe with examples of people changing minds and people changing other people's minds, but it requires the tools to do it. So what might those things be in order to help people change minds or look at alternative implementations of what they think they need? two of which I think pop up a lot are this notion of packet authentication or auditability. Doesn't have to be source routing necessarily, but the idea that I can take account for where a packet goes and in what order, at least then I can stand on a podium and say, please come and check it out. I can prove it. Dave Aran a couple of weeks ago said all of the clean slate stuff, none of it translated back. And I suppose that certainly none of it translated back to IP, but one that persists is the Scion network. There's implementations, it's all in software, it runs successfully in Switzerland, and there are some good ideas in it. Certainly I've started to look at it and people that I work with. And it's got some really nice features. And maybe we should think about how to do this on a global scale. The other one is the notion of client region. So we push for more and more privacy, which we should absolutely do. But I think we kind of maybe have to stop and ask ourselves, is it reasonable to expect that communications can be completely opaque without some kind of pushback? And I claim one of the things that we might have to give up is a trusted source for where a client is, not necessarily on street level, but certainly in terms of jurisdiction or region. And just as evidence of this, so Apple's private relay product embeds in it the location because of what we call internally as the pizza problem and the BBC problem. And the pizza problem says you make a connection to a service, but the IP address shouldn't, but unfortunately people have ascribed this notion, doesn't tell the service where you are in any way, shape, or form. And yet people, when they load up a map service, for example, and say, where's the pizza nearby, have that expectation. And that can't happen if there isn't some indication of where the client is. The BBC problem for us is the notion of the copyright problem. So people who are trying to move their connection initiation points all around the planet to watch different programs, for example. The reason we say BBC is because it's a free service. Historically, you didn't need an account to watch BBC streaming. You do now, which is a way around this. So that's one.
Okay. Marwan, one more minute, because I want to make sure, we all want to make sure that we've got time for questions.
Okay, so we're both 5 minutes. Yeah.
This is the 1 minute, and I claim there is a third stack now that is worth working on. The first we know of is the IP stack, end-to-end protocols at the top, point-to-point at the bottom. For better and for worse, the internet application stack emerges with applications at the top and the network at the bottom. So the two don't need to know anything about each other. But, you know, when you hear the words like centralization and consolidation and all of the rest, I would challenge that and say, I don't know of any example in human history of a global infrastructure, a large infrastructure that doesn't have some notion of this property. And we should be thinking instead about what this actually means. So I think what is emerging is the infrastructure services stack, where there's an open internet on the top and privately managed devices and a bunch of backend services that are not publicly routable and private networks. And then there are all these companies that provide services in between. And there's a set in common notions of caching, denial of service protection, some notion of zero trust, and so on. And now this begs the question, maybe this is a new narrow waist. And if so, what are the services that belong here? And what are the abstractions and interfaces between them? And I think there might be something interesting to think about going ahead as a model for an infrastructure. There's all kinds of implications to doing this, and I'm happy to talk about it. That's it.
Okay, thanks, Marwan. I mean, the bottom right plot is very interesting. That's a very interesting way to redesign the waste, the internet waste. Okay, so I think we're going to questions now. Jim, thank you very much to all speakers. Very interesting information. In fact, everything converges. I mean, for me, the main thing I struggle with is the fact that we try to optimize our network for many parameters, and that we know it's NP complete and it's going to be difficult, and there is no free lunch. Okay, if we optimize for latency, something else will pay the price, and vice versa. And we're in front of the complex problem. The only thing that I think is key is observability. And we have not been very good at that in the past in many companies. And observability, and more than observability, the fact that you can make recommendation and act automatically on what you observe. Because I remember a friend at Technicolor telling me, "Oh, you guys are good to observe, but you're not good at making decisions." And I thought that was a very smart comment. Okay. So, Jim, do you want to go through questions, please?
Oh, sure. So maybe the first question, we'll take a question that came in through the Q&A from Patrice Senac. And I think, Dina, this question probably came in when you were talking about the softwareization of 5G microservices, but I think it also related to what Nandita was saying about the importance of latency and delays. So the question is, what are the methodologies? So this is talking about performance and SLAs. What are the methodologies used to ensure that the functional and so correctness, but the non-functional, meaning performance such as latency, properties of large-scale container-based networking architectures are satisfied? So I think getting to the customer, the need for certain guarantees just in terms of performance for something to be deemed even functional.
Yeah.
I think you touched on that. Nandita
Yeah.
did, Ramesh did too.
Yeah, and it comes down to three things. First of all, the 3GPP essentially standardized finite state machines. You know what happens first, you know what happens second, you know what happens third. As a result, there is a very important modeling exercise that you need to do in order to understand the load that the different components will have to deal with under different types of conditions. Traffic models are essential in this case. What do you expect the mobile phones to be able to do? Are they going to be, 4G connected, 5G connected? Are they going to use data? There is a lot of work that happens in acquiring the right inputs. Usually we get them from production networks or the assumptions that the operators have with respect to the type of traffic that they need to accommodate. Performance modeling is essentially trying to come up with what are the transactions per second that each one of those microservices needs to sustain. It becomes a very well-defined computer science problem to go and say, what do I need to happen for those latencies to be able to be met? And then there is a very intensive performance experimentation, Patrick, that is happening. That takes a significant amount of cycles. Actually, the product that my team is launching is running across a number of operators, one of the largest operators actually in the US. Believe it or not, we have actually replicated a full stamp of one of their data centers, clusters, where our function is going to run, and we just subjected to what we consider is the maximum amount of traffic that they will need to sustain, and we go and we measure. And final, which is not going to surprise anyone else, we are putting buffer in the system so that it can absorb bursts, it can absorb failures, not an excessive amount of buffer, like the networks that we used to run, 30 years ago, but there is a certain amount of buffer, that is designed into the system in order to be able to absorb, situations where, things are not going according to your models. Last thing that I want my team to do, and we do in a fair manner, because typically we run software inside operator networks that we do not have access to, not the same as what happens in Azure, is we read data from the operators, and then we are going to say, is what we assume that's going to happen through our model happening in production through tracking a certain number of key performance indicators that we are essentially estimating through that modeling part. This provides a feedback loop that tries to essentially help us correct assumptions that were not proven to be, real in actual deployments.
If I may chime, if I may chime in quickly, great set of answers, Dina. I just wanted to build upon the last point that you mentioned, that one of the challenge as infrastructure providers is ultimately performance is something that is critical to the application and can be measured very well at the application, but often infrastructure providers don't actually have direct access to be able to measure, like, for an application op or an operation, what does the latency actually look like? So I think we actually resort to either proxy measures to what the application might actually see, say instrumenting the parts of the stack that we can actually have visibility into and control, so as to speak, or resort to some sort of probing-based mechanisms, right? And I think, this continues sort of to be a broader challenge for infrastructure providers.
If I can add just a little bit of color to it, Yeah, I completely agree that tail performance is what matters, and it's always been that way. Internet works well on average. So I just wanted to make a couple of comments. One is that performance is a moving target, and it's always been that way. We wrote a paper in the early days of the CDN, which was called the 8-second rule, which said that if your page doesn't download in 8 seconds, then people will move away. Soon it became 4 seconds, and then it became sub-second. And now we're looking at applications like, interactive videos where the latencies have to be in the 20 millisecond range. Otherwise, people may get cybersick. So performance is always a moving target. And it's also important to remember that performance has to be linked to business goals. In the early days, we used to do conversion studies, which basically tried to show that if you don't have performance, people will buy less. Or they will not add things into their shopping cart and things like that. And relating system performance to actual business outcomes is actually a very important area. And I think, we made some progress on the research side to answer some of those questions, but that's something that is very important to understand. Like what actually, ultimately it's the business that matters. And like, how does it impact the business? How does it impact users? How does it impact monetization? So the link between those two things, I think, is extremely important.
I would say, Ramesh, especially because performance costs. It's not something that comes for free. You need to invest in it. No, so there needs to be a significant return on that investment. Otherwise, you're just essentially spending a lot of cost
Exactly.
for very little in return.
That's right. And we ran into that even in the early days. We used to say, we can speed up the web by a factor of 2, and some people will say, oh, that's great. And some people will say, would that make people buy more? And so that question is a very important question.
Let me ask a follow-up question to that about performance costs. And when I hear the three of you talking, you talk about we, meaning your company, and optimizing those services. And to me, that speaks to something we were talking about at the very beginning, this notion that there's not a lot of internet, if you will, between your services and the customer at the end, because you have so much opportunity, and that gives you the opportunity. And maybe it's because you need that opportunity to optimize and to be able to innovate with maybe only, we were talking about the flattening of the internet and only a couple of hops, and the fact that some of the hyperscalers can reach 80 or 90% of the endpoints without passing through a tier 1 or a tier 2 ISP. So is it because of that business reason and the need to do that performance tuning that you're taking a lot of that into your own operations as opposed to letting the open internet provide that to you?
Speaking from sort of more of an Akamai perspective, yes, because we have to be close to the users, to the edge, to provide, application performance. And you do want to control all those points where you can provide performance. It also makes the system very complicated, and it's not an easy problem to provide the performance, even if you own a lot of the touch points.
So I can add to that and say, think about the black box that we're all taught, right? If you can't control the black box, you have to build solutions around it. And just for clarity, because we're talking about money and customers, I think it's important to actually agree on the right jargon. A lot of people think the customer is the client that connects. And actually, this is one of those follow the money where the customer for these types of operators is the service on the back end that wants to reach the clients. And every one of us cares deeply about the clients, but ultimately it's because the customer is paying. And the control issue is right. Of course, you have to build a system that there's a long article at Cloudflare. There's a history of the ECMP and consistent hashing in the routers that were being used at the border. It turns out that the consistent hashing functions were not as uniform as people thought, and there was no way to change them. And so the question is, do you invest in changing the physical infrastructure and relearning everything? Or do you build a separate system to compensate or give you back some control? And in that case, it was the latter, and it produced a system called Unimog, and you can read about it. And there's no layer 4 load balancing at Cloudflare. It's that every connection that comes in automatically gets redirected to another service before it hits the kernel. And that's how load is distributed in the Cloudflare data center, all because the border router doesn't do the load balancing that you expect.
Okay, we're going to need to wrap up because everybody starts to flee at the hour. Any last comments from anybody? We want to just talk for a second after that about what's coming up in 2 weeks. Last comments?
Yeah, I can go ahead. Based on the conversation around observability and diagnosing, triaging issues, I do find that the industry has made a lot of progress with. I know I would say something that is banal. Artificial intelligence and machine learning is helping a lot. I see it inside Azure. Tremendous progress. We have made progress to the point that we can automatically read 3GPP standards, understand what is the exchange of messages that needs to happen, and apply that knowledge in triaging issues that we see either in our tests or in production. So I'm super excited about that combination of artificial intelligence, machine learning, and networking data that is hopefully is going to simplify some of the things that we discussed here.
Mm-hmm.
A huge plus 100 to that. I think there is, there are a bunch of things that networking needs to do for AI ML, and then there are a bunch of things that AI ML can do for networking. So it goes both ways, and super excited about what's to come. Yeah, it's can't be a more exciting time to actually work in networking. Yeah.
I'll just say a word about what the original goal of Whale Watch was, which we created 25 years ago. The idea was that when a customer calls, there is a CCAR ticket, customer care ticket, and the ticket has all the data and the diagnosis of what happened. That was the goal we started out with. I hope AI and ML can get us there, but it's still a bit away. But that's really the holy grail. That everything, the data is there, the reasoning is there, the root cause analysis is there, and you can tell the customer this is what happened. That's the goal, but we're still far from it. But I agree that ML can help us get there to some extent.
Okay, I'm going to caveat everything that was just heard with a quote from a research intern that we had, which was, on the other side, everybody thinks if I could just be on the industry side, I would have all the data and all the answers. And he said, and nothing could be further from the truth. I'm going to leave it at that.
Great.
Jim, if I can, just the last one to answer Ramesh. Okay, I agree, but my experience with customers, and this is an experience in the past 25 years, if you go and tell them that there is a problem, they don't care. What they want to know is how to solve the problem. So we have an obligation to solve the problem for them, or to tell them how to solve the problem. Okay, or they will not use what you tell them in terms of telemetry and observability and all your root cause, okay? And now about machine learning, remember that machine learning is just about statistical learning. I prefer that word. I don't like ML, I don't like AI, okay? So when you train an algorithm, you train on data. If the data is the way your network works since 20 years, you're gonna just do the same thing in a different way, okay? You're not gonna do anything new. So for me, ML is very useful, it's great, but you have to be super careful, okay? Because these days it seems that ML has to be everywhere and it becomes a solution in such a problem instead of, we have been doing, Dina knows that, okay? We have been doing statistical learning for 20 years now. Our PhD was about that. And sorry, 10 years for your PhD, Dina. And we need to be very careful, okay? It's a super dangerous tool. It's very powerful, but super dangerous at the same time. Sorry, I shut up.
Okay, well, with that, we've hit the top of the hour. So let me thank, Christophe and I wanted to thank all four of you for being here. And in particular, bringing the perspectives that you've been bringing from industry, your experiences there into this conversation. It's been really great. I want to say to everybody that the conversation continues. We have a Slack associated with this. Christophe and I will send reminders to to folks to join the Slack. If you have other questions, there were a couple that came up we didn't have a chance to get to. We can talk about those things in Slack. And with that, again, thank you, Nandita, Dina, Ramesh, Marwan, fabulous, just absolutely fabulous. I want to remind everybody, let me share my screen here, what's coming up next. Our next event happening in 2 weeks. No, actually, I think just next week, now that I think about it, because we're off because of a holiday schedule. The next event is large ISPs, how do they work? And this is really sort of one of our more hands-on-y or how does it work type of discussions. What are the challenges they face and what are the engineering and computer science skills, some of which we've talked about today, that ISPs need? So
yeah,
with that,
I didn't know they still existed.
That what still existed, Christophe?
Large ISPs.
Oh, large ISPs. Okay, gotcha. They still do, and we'll hear from them, and we'll tell Jason Livingood at Comcast that large ISPs don't exist. Okay, so thank you everybody for tuning in to this networking channel, and thanks in particular again to our 4 panelists here. It was awesome. Thanks.
Thanks, and bye.
Thank you. Bye.